Hello and welcome to Bitewise. Today we're covering episode 2 of the 21st Century Timeswitch project. In this episode we'll look at WebSockets, network time protocol, building an internal clock for the ESP01, and we'll look at the mysterious SPIFFS and structs. In episode 1 we examined the ESP01 module. We designed this circuit which enables the module to connect to a relay, switching appliances remotely. We then built the design onto a circuit board, and that enabled us to test the hardware and develop various pieces of software to run on it. We're going to use WebSockets to improve the interactivity of the web interface. WebSockets enables fast bidirectional communication between the browser and the ESP8266 without the need to refresh the whole page. This new JavaScript code enables the browser to communicate via WebSockets. The code within the quotation marks here actually runs in the user's browser, and this adds a level of complexity to design, coding, and testing. This code runs when the browser receives a WebSockets message. We'll expand this in later videos, but for the moment there are only two responses: to confirm that GPIO2 is on or that it is off. When either of these messages is received by the browser, the code updates the text on the screen, and this is done without the need for the user to do anything. The switcher function is called when the user presses the on or off button on the browser page. All it does is send an on or off message to the ESP01. Here, I'm adding the two buttons on the page. They are both simple HTML buttons that call the switcher function. The off button passes an argument of 1, and the on button has an argument of 0. This new function processes WebSocket events as they arrive at the ESP01. It inspects each incoming message and undertakes different tasks depending on the message type and content. This section processes incoming text messages. At this stage, these are just the on and off messages from the browser. The code is very simple. It just compares the incoming text to two possible messages and reacts accordingly. Here we examine the current state of GPIO2 and pass the status back to the browser. This enables code on the browser to update the on-screen text. This code in the setup function runs when the device starts and sets up the WebSockets capabilities. This code calls the WebSockets loop function on every loop, which processes any events that have occurred. This additional code sends messages regarding the present status of the output when the output has just been changed manually. Finally, we need a couple of variables to track the WebSockets connection. Is it active, and what is its ID number. Finally, we can test the project so far. When the manual override button is pressed, this toggles the output and also updates the current status on the web page. We can also operate the output using the buttons on the web page, as seen here. NTP, or Network Time Protocol, allows a device to request date and time information from servers around the internet. There are some limitations. For example, it's not possible to request time information more frequently than every 4 seconds. In addition, the service is obviously only available when we have network access. So in the event of minor network problems, we need some alternative mechanism for timekeeping. For that reason, we'll need to run an internal clock for the project and also to synchronize the NTP clock and the internal clock to make sure that they're always in step. We'll start as usual by adding the relevant library, in this case the UDP, Universal Data Protocol library. When we make an NTP request, we're contacting a physical server located normally in our own country of residence. This global NTP path name should be effective in every country around the world, and the local server infrastructure will direct the request to a relevant local server. We'll add a few constants and variables that will support the NTP functionality. We'll also set a timer that will regulate how frequently we make a request to NTP to receive the time. We'll define 2 functions, one to receive NTP information and a second one to send NTP information. In both cases, there are defined formats for the data that we'll exchange with the NTP server. When we send an NTP request, the first thing we have to do is to ask the system to assign us a server from the available pool of servers. This helps spread workload around the system. This code sets up the packet buffer array with the pre-formatted data that's required to specify a standard time date request. With that code in place, we can now download to the device and test it. The response will be in the format of a Unix time, which is based on the number of seconds since the 1st of January 1970. We'll use an internal project time base of the 1st of January 2001, and this NTP time response is the number of seconds since midnight on that date. We'll use the millis function as the basis of our real-time clock. This function counts the number of milliseconds that have elapsed since the module was last restarted. We'll need to superimpose the millis count on a larger variable in order to enable proper timekeeping. We start by creating the variable RTC_bigClock. This is a 64-bit integer value that provides for centuries of potential timekeeping on the basis of accumulated milliseconds. RTC follower is intended to track elapsed milliseconds from the millis function and detect and account for rollover. For ease of testing, I've deliberately restricted RTC_follower to a maximum of around 1,000,000 milliseconds, which is about 17 minutes. And we need to ensure that the value is captured at least every 17 minutes in order for the clock to properly function. Here I'm creating a conversion function that enables the standard time base to be converted into a human readable date and time string. RTC_update clock is a critical function that enables values from the millis function to be traced and stored into RTC_bigClock. This part of the code detects whether rollover has occurred and transfers the rollover value into an additional increment to RTC bigClock. Because this function runs frequently, it needs to be kept as small and lean as possible. Here I'm adding code to the NTP receive functionality to synchronize the two clocks. The principle is that the time offset between the two clocks will be set when the NTP time is first retrieved, and from then on it will be subject to micro adjustments depending on whether the difference in the two clocks is significant enough. The reason for this approach is because I don't know what effects network delays or other factors might have on the consistency of the NTP clock, and I therefore want to make the logic slightly fuzzy and slightly soft in terms of adjusting the two clocks together to avoid gaps in the per second timekeeping. This section is simply temporary test code that enables us to evaluate the clock synchronization. This is the test output, and you can see that the system is set up to query NTP every 30 seconds. The first query doesn't occur until 30 seconds after the project has been restarted. That's intended to enable Wi-Fi to settle down prior to making the first network request. From then on, we query the NTP clock every 30 seconds, and you can see both the integer date time and also the human readable equivalent in the test output. SPIFFS allows us to place files on the flash memory of the ESP01. It provides a variety of file handling and directory handling functions. Structs allows us to create a template where we can logically group multiple related variables. In this section, we're going to create a standalone program that will initialize the SPIFFS file structure and create a file in which we'll store the parameter settings for our project. This will provide the basis for user-managed parameters via a user interface later on. Here, I'm defining a struct which contains all of the parameter variables within it, and this will be the basis of storage of those variables onto the flash memory via SPIFFS. I'm going to use an identifier string for the data so that the project can test whether the parameters are valid and consistent with the current version of the code. Here I'm going through the various stages of formatting the SPIFFS area and the various file functions that will create the parameter.bin file and populate it with our parameter data. Here I'm reading back the data from the parameter.bin file in order to present it on screen just to validate that it's been successfully written. Before using SPIFFS, we need to specify the size of the SPIFFS area in the board manager. Coming soon on Byteways, we'll complete this project in these 4 additional videos. Future projects include a red LED retro atomic clock, a home automation hub that will allow multiple time switches to be connected together and operated via infrared remote control, an Amazon compatible power switch, and what could very well be the world's cheapest computer. If you've enjoyed watching this video, don't forget to like, subscribe, or leave a comment. If you've got any suggestions about future projects, please make a note in the comments. And don't forget to hit the bell icon to receive notification of future videos.